Hey there, welcome back. So let's run this case, the channel. So previously we did the setup just to show you how to set up the period boundary conditions. Now I'm directly reading the solution. So remember that here. So what I will do, I will go for runs, URLs, and LES, and then DNS. And I'm going to show you a few scenes, a few actions, but I'm not going to run the whole stuff. So remember that when you open and you see init means initialization, everything zero, final, you have the final solution. So most of the time I will go directly open the final just to show you. Okay, in this case I'm opening the init, the initialization of the runs case. Okay, so it will be exactly the same for all cases, but it's going to change. It is the Turbulence model. Okay, so just to point out that the setup is pretty much the same. So remember that you go here, well, in runs is steady. Okay, so we put steady there. When you move to a scale resolving will be transient. Remember also scale resolvers are 3D. So we move here, you set up your model. For this point I would set just k omega, this one with this correction. We know how it works and everything. And again, materials. So you here have the description, the properties that we want to get this shared Reynolds number. And to point out something about here, boundary conditions. Again, we already addressed this one, but just to point out how here you go here, you set it, and you have here the periodic condition, and you can select your pressure gradient. Okay, so in previous video I think I put 1, but it doesn't make a difference. -1, 1, it will be the direction that it moves. So I wanted to move in the positive direction set, so you put here -1. Okay, it will reduce, and this is the one that it will move it. Okay, but doesn't matter. You have two options, and also mass flow is up to you. So this is the case setup. What is important? Okay, and I want to stress this when setting this simulation. So this is the runs, but when we move to the LES or DNS, you need to set up all your monitors. Okay, you need to monitor many quantities. In this case, we set the monitors, but we're interested in this wall shear average and Y plus average, or it should be average instead of maximum. Okay, remember, so let me check this definition and put here average. Okay, so we're set up here. I will press initialize, and now I will go and let me run about 100 iterations. Okay, so we use the standard method. Okay, so let's say I recommend when you are running steady, okay, using what is proposed, the default one, it is okay. So decouple. Then when we move to transient, it's better to use something else because this is very expensive. Okay, it uses a lot of resources. So this is all. Okay, so I will run 100 iterations. Now I will write the files that I would like to overwrite the files that I have there. So it was asking me if I want to overwrite here. So as you see here, time series means that you already have a solution there, some files. Okay, that I run like 2000 iterations. So see that we're running here. This is the runs. So the idea is following with this workflow that first you start with the runs. You compute integral length scales, you refine your mesh according to your physics that you're getting. You get also some insight about the physics, what you're doing. Then you move to URLs using the previous solution. So just to refresh your memory, okay, about that. Let me go here. Okay, and show you that workflow. So it will be this workflow. Okay, so basically you start with the run simulation. Okay, you compute integral length scales, get an idea of the mesh. This is a good one. Okay, check the physics, everything, and then you move to URLs. In the URLs, you get a good initial condition, and with this good initial condition and a better mesh, computing integral length scales and grid refinement ratio, you move to the scale resolving, and that's all. Okay, so that is a recommended workflow. Okay, and okay, in this case, it's running. Let me go back here. So I'm here, okay? So just to point out also here, I put the interpolation files, okay? These interpolation files also, I let the simulation run a lot. So here we have a final solution of a runs, a final solution of a runs, of a LES, and so on. So look that running here. So we have a average y plus. Okay, I changed this one, something about 9. So we're there in the viscous layer. Probably it would be better to make it finer. But look, the wall stresses the wall, so it's approaching asymptotically to the value that we are expecting. Okay, so this, as you see here, this will take a long time to get to that value. Okay, so what I want to do here, okay, is almost there in 100 iterations. So I will go and will open the final solution that we have there. Okay, but also we'll copy this time series. Okay, we'll use this time series to replot these variables that we have there, just to show you what's happening here in the runs. Okay, so I put it there, have there. Case data, let me open final. Okay, so we're here, and I want to show you, okay, so let me plot here just to take a look at solutions. So see that this is an average solution that we have. Okay, so probably you don't identify this one with what you have seen in theory, because that one is, and let me go and just plot here. Let me go here, and that one should be here. So the runs is just an average solution. Okay, in reality, probably you have seen some papers about this one. Is this what you have? Okay, but in the runs, we don't capture anything about these streaks here. Okay, we're capturing the mean behavior. So see here, when we compare the mean, they are very similar. Okay, so this is what we're doing, and the runs is good, given that you see basically it's getting the exact solution that we know here in about 3,000 iterations. Instead, the others you need to iterate for a really long time. So this is what we have. This is the velocity profile. Okay, and let me plot the monitors here. So residuals, that you have that information there safe. See that these are your residuals, and see that it's actually 7,000 iterations. Even if it's a simple problem, you need to let it run a lot. Okay, in this case, and also we have these plops there. So let me plop this one. Okay, it's reading the file. Okay, this is, see that we're maximum by plus something about 8. I don't recall it's maximum and average, should be maximum. And if I plot this one, see again here, see that it's approaching very slowly to 1. Okay, actually I need to run more longer. Okay, but see that it's approaching there very slowly. Okay, so this is the idea. But what is interesting, remember that to generate those interpolation fields, so see that here we already have a solution. Okay, and this solution can be used as a starting point for the next one. It can be a quartz or finer mesh. So you can generate those interpolation fields. To generate, then you go here, interpolate, and just write data, choose your data, and that's all. Okay, so domain, and then you create, I will call it inter1, and that is your interpolation data that you can read in the next case, in the next mesh. Okay, so this is the way I would like to work, and it doesn't matter the solver that you're using. Okay, they all will give you this option now to interpolate data in this way. Finally, just to close this case, so see that here we have this field, this solution, but also we can add a perturbation. We can perturb the solution, and that will be a much better initial condition for the runs. So to add a perturbation, remember that you go here again in the text user interface, and now it will be solved initialization. Okay, and here see that you have this condition init term bool. So we use this one, and that one will add their perturbation. See there, it's adding a perturb field, and now this is much better starting point for a scale resolving simulation. If I put this in the runs, immediately the runs will smooth all this, okay, fluctuation. Same will be for the URANs. The URANs will smooth this. Probably will conserve something, but you are not going to see anything. We're not going to see those streaks there okay, because everything has been averaged by the model, okay. So at this point, this is the runs, okay? This is the first step. This is one you can go ahead and compute your integral scales, everything, verify that. I'm not showing that here, but just to compute the integral length scale, you will go here and create those new fields and so on. So now let's move to the URLs, okay? I will go and I will open the final, okay? And let me go here and URLs, we have time series, okay, so let me open. And the point here, okay, see that we have a solution here, okay. So basically this is a solution obtained from the runs, but you want also, you can perturbate it. You will see that the URLs will also smooth those fluctuations. Unless you use a very small mesh, you are not going to see those fluctuations. The thing that I want to point out that now it is unsteady, remember, transient time step. Here you set transient, and then when it comes here to setting the methods, okay, you choose. So usually it's a good idea to go for second order, and this option, non-iterative. This is the one that it will advance much faster than the standard, like this, iterative, okay, this will advance much faster. But remember that you need a CFL number less than 1 for stability reasons. Do not initialize because you're starting from this, or you can choose and go interpolate and read and interpolated data. Just to show you, you go like this, you look for the data. So just to show here, so see interpolation fields, and let me read this field. Okay, this is the field generated from a DNS, and see that when I interpolated, okay, what did I do? Okay, let me read. Okay, interpolate. Okay, so I think I read the wrong file, or it's not written. Okay, read interpolate, and okay, somehow it's not written. Okay, let me, later we see this one. So the point here, we're in the URLs, and here in the numerics, be careful that this case we're going to run, but to get also an estimate of this time step, okay? So if I launch this simulation, you're going to see the time step. Remember that here now you need to set a monitor for the maximum CFL. So the idea is also in this URLs that is very stable, we can play around with time step and get the ideal time step to move to the LES. So in the LES, we know that it's extremely recommended to have a CFL about 1. So this is a rather large value, okay? So if you run this one, I'm not going to run, but if you run this one, you will see that your CFL will be really high, but the URLs doesn't have problems, okay? So you can do that. Okay, so see that this was run for a really long time, 100 seconds to get all the statistics, okay? And if I go here, so remember that you can plot the Q criterion, and here I have the isosurfaces of Q criterion, but you don't see anything because those structures, okay, actually I didn't put it, those structures doesn't exist here. We don't see those structures here. So what I wanted to show you, if I go here in monitors, and where, so see that I set many here, many monitors. So see that in custom fields, you have the custom fields. So I have my Reynolds stresses here, normal and well, just the normals, the resolve kinetic energy, tau velocity, u tau, u plus. I compute that, all those quantities, because I can do that plot, okay, the normalized velocity plot. I can do it in this case. I will show you later. Okay, so let me plot residuals, plot. So see that these were my residuals, and we can also plot this quantity. Okay, so it says that there is no data. Why? URLs. Okay, I think I'm reading the wrong case. Okay, let me go back. Final. Okay, this is the right case. And this file, let me see. Okay, yeah, I have all the information there. So it should be working. Okay, I don't know what was the issue here. Okay, so now, and let me go where I was. Okay, let me minimize here. I want to plot this one. Okay, why it's not plotting? There is no data to plot. So the monitor, the residual plot. Okay, but this report plot. Okay, let me see this one. Okay, the data. Okay, it's not reading the default data, but I can go here and use the post-processing tool plots. Okay, and let's plot the data using this tool. So I would plot the wall shear stress, plot signal. Okay, and here we have the wall shear stresses. Okay, automatic, and see that these are the quantities. Okay, so this one, okay, is strange because it's just showing me that, okay, I have like the last seconds of the simulation, so likely I think I override those statistics. So let me see here, what do I have here? Yeah, no, I have it from 1 to, yeah, I should have all my statistics there. So let me copy this. Okay, put it here. They are there, and let me go low input file, INU runs, and let me read this one. So, okay, so now I have the complete signal. Okay, and Y is cutting. Okay, I have access. Okay, so plotting here is just showing me the last part, but click to run. Let me go for it. Okay, this is strange. I don't know why it's not plotting the whole stuff. Okay, so I have the complete signal, but it's not plotting. But anyway, probably in the next one we're going to see. So the idea here is that we have this. Okay, and just to show you, I can go again and let me add the perturbation here. So see that I added this. Okay, and again I don't see the perturbation. Okay, so let me go here. So usually, let me see, bam, init turn. Okay, and velocity. Oh, okay, I was plotting the, I think I was plotting the average field. Okay, so sorry about that. Okay, sometimes happens. Okay, so let me go back here. Okay, so just the solution, and then I add this perturbation here. Okay, and the velocity. Plot here, and be careful, it's not on a steady statistic, it's instantaneous values. Here you see that you have your field. So now you can write this field. Let me go write export, no, interpolation, write data. I will call it like init, like this. See that I wrote this one, and let's say that now we move to the next case. Now, so now let's move to the LES case, and let's imagine that in this LES case we're using a finer mesh. So the idea here would be, when you move here, LES or DNS or whatever, we'll open the initialization. Okay, so in this, we don't have anything. Okay, so basically we choose the model. Okay, so it's up to you to choose any model, and this one is running the well. Okay, but my recommendation is go for this one, the kinetic energy. This one, the one equation, is a dynamic model that it will give you information about the subgrid scale kinetic energy. So I read this one. I go here. You see that you have nothing. And if I go here, interpolate, read data, just look for the data that we just saved here, this one. And imagine that this is a finer mesh. So we're coming from a coarser to a finer. So it is doing that interpolation, so velocity here, and see that you have that field. So now this will be your starting point from your runs. Okay, so this is a very good initial condition. And usually when you do these channel problems, you need to add something like this, because otherwise immediately everything will be damp, or you will need to let it run for really long times. Okay, so usually it's extremely recommended to do this stuff. And let me move this information here. Okay, I know that actually I was working in the wrong folder, wrong directory. So that's why I wasn't reading the files previously. So let me go DNS, Fluent case, we're here. Okay, let me move all this time series here. So see that I run for a really long time. See that this file is starting to become large files. Okay, so now that I have that, I can do some plotting. Okay, so let me go. Okay, let me show you that you set up everything, the case, whatever. Your method, see that here I'm not using couple, I'm using these methods that are more economical. This is what is recommended. And see that we're using also a good, robust and accurate numerics. Okay, so here is not desirable to use stuff like second order win. You need to go for bounded central difference or central differences. When it comes to controls, standard values, set up all your monitors here. So see that I'm setting many monitors. So see that I'm plotting, see that information in all these points. So there are many points here, normal to the wall. So they are accumulating energy. Okay, computing statistic for everything. So you need to set up all those monitors that you have here. Okay, those derived quantities. So see that I have UU, VV. These are the normal Reynolds stress, the resolves to calculated energy, shear, Reynolds stresses, velocity fluctuations. Okay, so I put many monitors, many quantities to control. Okay, so this is important. Do not forget to do this one, because scale resolved simulations are about this, about getting those statistics. Okay, and after setting all your monitors, you can go, okay, and run your case, okay, with no problem. So see here, I will launch. Okay, I will override those files just to show you the couple initial iterations. Okay, and see that it will start to do everything, the first iterations, and computing all your statistics what I want to plot. Okay. So remember, we're starting from a very good initial condition, but even though we have here this monitor, the shear stress, so see that we have this, that is not starting precisely, from one. This is the fluctuation that we added in the field. So slowly we'll start to oscillate, and it will take a really long time now to get those statistics. Even if it's a small mesh, relative simple case, you need to run for really long times to get good statistics. Okay, so let's imagine that we arrive to 100 seconds, and let me open this case, the final solution. Okay, so let me get again these statistics. I'll copy that there. And just to show you the final solution after you let this simulation run for a really long time, and that's up to you. Okay. See that this is their instantaneous value. Okay, so we're in 200 seconds actually of sampling. Your instantaneous velocity, and then you can look at all your statistics. Okay, resolve K, mean velocity, whatever. So let's look at. So this is Bx prime. This will for me will be the fluctuation that actually there is something there. Okay, yeah, I need to gather. I didn't gather those. These are the fluctuations, and you have mean quantities, mean velocities, everything. So okay. So that being said, okay. Okay, the last part that I want to show you. So the monitors here, if I go here, residuals, plot. These are your monitors, so see a lot of iterations, so about 40,000, more than 40,000 iterations. And we can plot this one. Let me plot this one, for instance. Plot. Okay. That is not plotting because the data should be there, but let me go here. And I want to load the data for the wall shears, this one. So it's reading the data, and now let me go here, plug the signal. And this is the signal. So see that starting from 0 all to 200, and see that these values are oscillating. So I don't want to use the first 100 seconds, so click to range. I don't want to use the first 100 seconds. And this is what we have, okay? So we have a value, a mean value of 1.15. So this is very high, okay? This is about 15% of error, okay? But remember, this mesh is square, so you need to refine this mesh. So as you keep refining, you will get close to 1, okay? But this is, see that this is exactly the same mesh for less and runs urans. The runs urans will give you precisely 1. But then in these models that you are resolving those scales, okay, and you have a good mesh, a fine enough mesh, you are adding a lot of error, okay? But this is the idea, okay? So you have here everything. And for instance, remember that we can do some plotting of the normalized velocity profile. So in this case, I have a line there. I'm plotting in this line there. You see this line here. I'm plotting these profiles. And see that I have here also the Q criterion to visualize the strict lines, okay? So see that these lines are rather thick. They are not as nicer as in this case. Remember that this mesh in this case is a very fine mesh, okay? So it's about 2-3 millions, okay? So it's a very fine, so we resolve better the structures there, the coherent structures here, as we have a rather coarse mesh, that is what we're getting. But there you see, you have the idea, okay? So just to plot that velocity profile again, I have all the monitors, so I compute all the quantities there. So what we can do is here, I already put here my custom fields, Y plus, U plus, okay? And, okay, so, so let's choose, okay, so, so here should be, okay, custom field and U-tau, okay? U-tau and axis, okay, so y, okay, apply. So so in this case, y is given this one. Oh, okay, yeah, I think, yeah, I run a couple of iterations, so I think I lost the data. So let me go to the DNS. Yeah, I think that is a problem. I said run, I erased my statistics. So be careful just to that. Do not override the final, because it may happen that you might erase those statistics. Okay, so let me go back here, and here I should have. Okay, so see that now I moved to the other U plus, Y plus. See that this looks familiar, okay, and let me load the validation data, okay, and let me put those profiles that we're used to. So I put it there and see what is happening here. This is the DNS data, and see that it's not doing the blending here, okay? In that position that we're sampling, it is fitting better the laminar solution, okay? So this is the problem here. This mesh is not a good mesh. So see that 15% of error also translate here in a deviation for this theoretical profile. Okay, so this is the DNS. Okay, and I can do the same. We can do the same plot for the LES. So let me go back to the LES if I didn't erase that there. Or yeah, I think it was the initial state there. So that was the DNS. So now let's take a look here. Okay, yeah, I lost that data. Okay, but let's go to, for instance, case, let's go now to the URLs. Okay, so I have there. So if I go to the URLs and I try to do the same plot. Okay, I have it there, and we need to put it in log scale there, and see that we have this, and you already start to see the difference here. So if I plot this, okay, I need to compute the right. Okay, I using the wrong scaling here, so I need to scale in the right way. But see that now when I translate it here with the right scaling, it will do the proper fit in here. Okay, so probably in the runs I have the right. So I need to revise this. Okay, I don't know why this is translated there. Okay, so I have the runs. Okay, in the runs. Okay, let me do something. Well, probably I'm using the wrong files, the old files. So let me go here and let me update those files. Or better, let me go and open those cases. So let me go here. So I think those cases I already play around and overwrite the information there. So I will go here. Fluent case, let me go URLs, let me open this. Okay. So at this point, I will go and here. And now this is okay. And I will put there. And see that now using the URLs, we have a good agreement. I see that is fitting very well here, your region. And here, remember, this is buffer layer, so here the errors are large, okay? So this doesn't mean by no means that this is wrong. And actually, we have the good solution. We have 1 Pascal when we average that at the wall. The wrong solution here will be at the actual fitting to this, okay? So just to recall, to show you that if you plot wall fluxes, wall shear stress, button, see that you have precisely 1. Okay, so actually it is the correlation that is wrong in this case. So see that is not universal, and you will see that different in the buffer layer where you have the largest errors. The same way I can go, and so I will update the data that you can download, but the problem is the previous data. Yeah, I overrode that data with something else. So now I'm opening the LES. And again, we go here, crossing fingers that we're going to get the right values. Okay, so I think there is a problem here. Okay, why? Okay, the LES is also, but the previous one, it was what I was using previously. It was okay, U plus. Okay, that was the problem. So now I have U plus. Okay, and I can load the data for comparison. Let me select everything. Okay, and if I plot here, see the difference. So you recall the DNS. The DNS was kind of trying to fit this one. See, this one is now a midway between this and this. Okay, so again, this is the model kicking in close to the wall, but still the mesh is not good enough. Okay, so if we plot here, you go here. So see, basically we're sampling here, but the mesh that we have in this case is not good enough to resolve well all these structures and everything. Okay, so that requires some refinement in the mesh, but to stress also that that refinement is not normal to the wall, okay? Not necessarily normal to the wall. Okay, it's also here, and it's also this span-wise and string-wise distance, okay? So maybe normal to the wall is okay now because the less it works with wall functions, but then you have this all other directions now, span-wise and strings-wise, that are giving problems. So the case that you see here, the solution that you see here is a quite fine mesh, okay? So look at here, it's very fine to the wall, so that's why it's giving much better results. So, okay, that's all for this case. So as you see, as you try to run this, it will take a long time just for the statistics, okay? But setting the case is relatively easy, okay? Here there is not all those options that you have when using the k-omega, the standard rank models. Here you just pick one and that's all. The important thing is just to choose a good numerics and then also your mesh, like the wall, okay? Usually you should resolve also the other wall distance units, namely delta X and delta Z. So that's all for this case. Thank you for your attention. See you next time. Bye.